Okay, this is now 4.4. Get the notes started. There we go. This time we're working with divisibility, so probably one of the classes, if you're some sort of math major, that you have to take is number theory, and you'll usually begin with stuff like divisibility. Okay, and we're still working with direct proofs at this point. It's just we're sort of each section will attack a different topic of direct proofs. And this one is about divisibility. Okay. Okay, so first off then, the definition of divisibility. D will say divides n if and only if there exists integer k such that n is equal to d times that integer k. Right? This notation is a little bit weird because usually we'll write, for example, 3 divided by 4, right? And this is kind of like in the other order. So it's more like you're saying, does 4 divide 3? Okay. So it's confusing at first if you've had this notation pounded into your head. It's not the same thing. Okay, so just be aware of that. In the informal settings, they'll say D divides N, or they'll say N is a multiple of D. Or they'll say N is divisible by D. Okay, okay, so let's take a look at number 4. And this will be a direct proof using the definition of divisibility. Okay, so they're asking, does 3 divide this big long product, 3k plus 1 times 3k plus 2 times 3k plus 3, where k is an integer. Okay, so what we're trying to see is if we can rewrite this expression here as 3 times something. Okay, so then the definition of divisibility, the object, this big long object that we're kind of working with down here, that is the n part up here. So we're trying to rewrite this as the divisor, this 3 times something. Okay, so this is our n, and this guy over here is the d. Unfortunately, we have this k, and that now we have a new k being thrown into the mix. That's unfortunate. Okay, so let's go at it. I'm not going to make this like the perfect proof of the century. We'll just jump to the chase and notice, sort of jumping to the body of the proof, skip the supposition. So note this 3k plus 1 times 3k plus 2 times 3k plus 3. What the heck is that thing, right? So it'd be 9k squared, first outer inner last, right? So on these two terms, 9k squared plus 3k plus 6k is 9k, and then plus 2. And then this is all times 3k plus 3. I have to FOIL that kind of out, or distribute, however you do it. 3 times 9 is 27k cubed. And then I have 27k plus 6k, and then plus 27k squared, and this should be a k squared. Where am I? 27k squared plus 27k plus 6, and then we combine like terms, so 27k cubed plus, what is that, 54k squared plus, that'll be 33k plus 6. And we're trying to write it as 3 times something. That'll show that 3 divides it. So we can, and that something has to be an integer as well, right? So we can factor a 3 out here. We'll have 9k cubed plus 3 goes into that one, 8 times k squared plus 11k plus 2. And thus, where this thing, this thing right here is an integer from what we were doing in the last section. It's closed under multiplication and addition and all that jazz. So hence the product, I'm not going to write it out, but the product is 3 times some integer and is thus divisible by 3. Okay, by the definition of divisibility. Okay, so that's kind of an intro problem where we are multiplying stuff together and then factoring out and showing that the definition divisibility holds. Let's look at number 15. This is a little more typical of what you would see like in the intro sections of a number theory class. We have for all integers a, b, c, if a divides b and a divides c, then we have a divides b minus c. So we want to show that. You could sometimes, a lot of teachers will say something like, we want to show WTS. We want to show that the definition is going to follow. So it'll be sufficient to show that b minus c equals k times a. So where k is some sort of integer, and that'll prove that a divides b minus c. Okay? So sometimes at the top of a proof, the teacher will write out something like that, and we want to show this. Let's get to the, I should be writing proof before I start my proofs, but here we go. So here's my proof. Right, so suppose A, B, and C are payback integers such that A divides B and A divides C. Okay. We want to invoke the definition of divisibility here. Okay, so by the definition of divisibility, B equals A times some integer, and C will also equal A times some other integer. Okay. They could be both the same, but we also want to allow for the possibility that they are different. Okay. For some integers, K1 and K2. Okay. All right. So now we kind of go to using axioms and definitions and addition properties and stuff like that. So we notice what is this B minus C thing. So note B minus C is equal to, by substitution, AK1 minus AK2. Okay, so that's just a sub. And then that'll be equal to, well, you can just use the distribution property to rewrite it as that. So we've kind of shown that what we wanted to show, right? B minus C equals K times A, where K is some integer. It's just we have to note that this K1 minus K2 is an integer. So I say where K1 minus K2 is the difference of integers, and therefore an integer, because the integers are closed under subtraction. Okay, thus B minus C is equal to A times some integer. Sometimes in the book they'll say let Z equal K1 minus K2, and then Z is a difference of integers and therefore an integer, and then you could say thus B minus C equals A times Z, where Z is this K1 minus K2, which is an integer. Thus by definition it follows, right? So thus by definition of divisibility, B minus C is divisible by A. Or if you'd rather just write it, A divides B minus C. Okay. Alright, so that's kind of the outline and the way most of these proofs will go. They're all kind of the same at the end of the day. Let's look at maybe one or two more. So let's look at number 22. A necessary condition. So they still are kind of trying to confuse you with the necessary and sufficient stuff. A necessary condition for an integer to be divisible by 6 is that it's divisible by 2. So in the previous problem, I don't think, or maybe the one before, I didn't really bother transforming it into a symbolic form. Here it's kind of necessary because you need to ferret out what that necessary condition does to the implication. Is it going to go forward or backwards or what? And you probably have to look back in the books to remind yourself how it works. But the way it works is this: for all n and z, if 6 divides n, then 2 divides n. Okay, and this is what we want to prove. So we'll suppose n is a particular but arbitrarily chosen integer such that 6 divides n, and then we'll invoke the definition of divisibility. N will equal 6 times k for some integer k. And from there we can play around a bit in order to, so what we want to show, maybe we should remind our reader, we want to show that n is equal to 2 times some other integer like that. Okay. Right, so for some integer k, we notice then that n equals 6 times k, which you can factor, right? So 6 is really 2 times 3 times k, and then you could associate, so 2 times 3 times k, where 3 times k is a product of integers and therefore an integer. Okay, so n is equal to 2 times some integer, which is what we wanted to show, right? So by definition of divisibility, two divides n. Okay. All right, so let's see. We got another one. Sure. Let's try number 27. And we have for all integers a, b, c, if a divides b plus c, then we have one or two things. Then a divides b or a divides c. Okay. Just a note that comes to mind when I'm working with this stuff, it's like intro to number theory stuff, basically. And why is number theory important? Number theory is kind of the basis for all cryptology that we used to do, probably from the 60s on. Now they do some sort of other kind of cryptology. If you call it a elliptic curve cryptology or something like that. This is probably what's used in your cell phones for security and stuff like that. But the people that employ a lot of cryptologists would be the NSA, and that is a job you can get. Probably more likely to get a job there now if you're a computer programmer, but they hire a lot of people. So as long as your background's squeaky clean, they have like a pretty comprehensive interview process. I went through the interview process, and you have to take just an entrance exam in mathematics. You have to do a lot of interviews. So like it covers like 4 days. You do an interview every day. You do a full psychological evaluation. You have to talk to a psychiatrist. You have to full FBI background checks. So past going back about 7 years, they send FBI agents to your house, and they interview all your friends. What else did they do? Lie detector test. I took 2 lie detector tests on 2 separate occasions, and they were not fun. Okay, they were like 4-hour long interrogations, basically. So it's if you can stomach all of that, if you can stomach like basically having somebody in your private life, then it's a great job. You feel definitely like you're doing something with your life. You're securing America and working for them. But it is a lot, and I don't think they hire. If you're not a U.S. citizen, you're probably going to be. It's going to be a lot harder too. But you can always go to the NSA website or even the CIA website. They probably do the same kind of stuff, and try to get an internship if that's something you're interested in. They usually recruit at if you go through to like a math convention or something, there'll be recruiters there. They were recruiting at seems like CSU. They were recruiting, but I don't remember. Anyways, we want to do number 27. 27 is a little weird because it's not true, right? And you kind of inspect it. In the book, they'll say, is it true or is it false? If it's false, you got to give a counterexample. So an easy counterexample, let's say let a equal 3, b equal to 11, and c equals to 1. Okay, so in that case, b plus c in that case is equal to 12. So 3 divides 12, but it's not the case that 3 divides either, and we could write not divides like that, just put a slash through the division symbol, but 3 does not divide b, right? So b is 11, and 3 does not divide 1. Okay, so it's not true by counterexample. The statement is false. So you'll see some of those in the software as well. So speaking of, not divisibility, not divisible, we have the negation of divisibility. And all you have to do is go back to the original definition and rewrite it with an existential and negate the predicate. So it was originally an existential, wasn't it? So where was it? There exists, yeah. So now it'll be for all integers k, n does not equal some d times some integer. All right, so d does not divide n if and only if for all integers k, d does not equal n times k. Okay. Another way of saying it, d does not divide n, is the same thing as saying n over d is not an integer. That'll work as well. And in particular in the homework exercises, that's going to be kind of it's the second definition that you'll probably have to invoke. So in particular, a problem like number 6 is 29 multiple of 3. Okay. In other words, if we translate that, it's asking, does 3 divide 29? Okay. So consider then 29 divided by 3. If you put that into your calculator, you get 9.6 repeating, which is clearly not an integer. So it is not a multiple of 3. Okay. From here, they look at the unique factorization theorem, which doesn't hold in all domains. Okay, so unique factorization. So I got really interested in computer aided software because I went from a time where we did everything by hand to computers doing so much of everything. And I was interested in how computers actually did integrals. I mean, one of my students was prodding me on. It was like, how did this thing work? How did these computers figure out the integrals and stuff? So when I got one of the first books I read on the subject, I didn't read it comprehensively. I just sort of skimmed it. One of the first books the algorithms that the computer uses to do integrals relies on unique factorization domains. So this is actually, it's in the applied work, but it's a very specialized area. So anyways, just to show you that it's not necessarily going to be the case that all numbers have unique factorization in particular domains. Imagine you're in the complex numbers. So you're working in the complex numbers, which they'll write C with this bar through it like that. And in that case, you could write 6 as 2 times 3. These are complex numbers as well. It's 2 plus 0i, and then 3 is the same as 3 plus 0i. So remember, the complex numbers allow us to have these real part plus imaginary part, and they're kind of like ordered pairs. But anyways, 6 times 3, you can also write that as 1 plus root 5i times 1 minus root 5i. Okay. When you don't have a unique factorization domain, this becomes a nightmare for your computer. If you have a unique factorization domain, you don't have to worry about 1,000 different ways to rewrite one number. Okay, you can just use this 2 times 3. Unfortunately, I think for integration, they do a lot of their work in the complex numbers. I don't remember if that's true or not, but it seems like that, which is kind of a bummer. It seemed like a lot of the algorithms would push non-unique factorization domains into unique factorization domains so they could take advantage of the properties of unique factorization. Okay, so hopefully that convinces you somewhat that there are applications involved here. But anyways, the theorem, without further ado, is the theorem, I think it's 4.4.5. Okay. And it just says, given, this is kind of a long one, so you may want to fast forward a little bit, but given any integer n greater than 1, there exists a positive integer k distinct prime numbers p sub 1, p sub 2, dot dot dot, all the way up to p sub k, and also positive integers e sub whatever, e sub 1 and e sub 2, dot dot dot, all the way up to e sub k, such that we can rewrite n as p sub 1 e to the 1, p sub 2 e to the 2, all the way up to p sub k e to the k, or e sub k. Sorry about that. And any other expression for n for n as a product of prime numbers is identical to this except for possibly the ordering of the primes or the factors. Okay, so a lot of proofs will sort of pin their hopes to this fact, and it comes up. Okay. Anyways, the kind of problems you work on in the homework. A lot of times they just want you to get the factorization, and one of them was like find the factorization for 20 factorial squared, and that was a bit of work, right? But it'd come down to rewriting this as a product of primes, and then multiplying all of their exponents by 2, right? So you would end up, I don't know if this is true, but it'd be something like 2 to the 5th times 3 to the 4th times dot 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 whatever times maybe 19, and that would equal then 2 to the 10th. You just multiply the exponents times 3 to the 8th dot 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 times 19, and you have to fill in the blanks. I don't know what it is, but that was one of the problems. Anyways, 37, use the unique factorization theorem to write the integer in standard form. Here's part B, 5733. So I'll put them in ascending order, and 3 squared times 7 squared times 13. Typically what you do is divide by primes all the way up to, so you test primes up to the square root of 5733, whatever that is. You'll pretty much find all the primes, and then you could use your calculator to kind of figure out. Yeah, your calculator may even have a factor button on there, so usually it's like factor 5733, and it'll just give you the answer. Okay, if you have like a TI-89 or something. I don't know. Number theory is an awesome subject. I can't say that enough. I loved number theory when I first saw it. It's like we're so good at doing arithmetic thanks to our grade school and stuff. And that's all number theory is about. It's working with integers, prime numbers all over the place. If you like looking for patterns and stuff like that, but there are a lot of proofs. Okay, so it's not just sitting around playing with numbers all day long. It's heavy with proofs. Okay, but you'll be proving things about prime numbers and proving patterns, and it's just a lot of fun. Okay, so anyways, we'll leave it at that. See you next time.